Thank you. So it's good that you got you by surprise, but you did a wonderful introduction to my talk. And can I have? Okay, great. First of all, I want to thank you for inviting me to give a lecture. And more importantly, I want to appreciate this Clinam organizer and so on, because it's get better every year in number and quality, and chapeau, really, great work. So I want to, given the short time and the pictures, given the short time, I want to try and really look on the big picture, as I said, like Monet here, and actually relate to the broad picture regarding the human functioning. And if we want to really look on the big picture, we really want to relate to the human being functioning and his surrounding as one functioning system. But this is a very known slogan that Klaus heard from me millions of times. And that was quoted by the NSF that really came up with this wonderful phrase at about 2001. And it was a big fuss and a big debate. Like Europe didn't want to listen about that. But the idea was, as the previous lecture was, that we have so information from all areas. Now we have even the technologies. But do we really know how to analyze all at the same time, various sources, various levels, and so on? Can we really look on the big picture like Monet, each one from his side? And so this was, I don't want to go, but I just wanted to give you the background of today. Today, converging technology is acceptable, but that was the beginning where United States was fighting Europe. Europe called it WICC, and the United States converging technology. And then we had some tailwind by Phil Sharp and others, but it's still not there. It's still more talking than doing. And nowadays, we reached peace gradually, and we have the EU-US combining forces, and all the world is accepting the phrase converging technologies. But what does it really mean? Where are we going? How far are we really converging technology? So the good thing is that science and technology has reached a really matured stage that they are providing the knowledge, the big knowledge, the small knowledge, the technologies, and the tools. So we have it all. We have imaging tool, and we heard at the previous lecture, we have various tools. But the idea is to take all these tools, first understand mechanisms, but if we want to move it to personalized medicine, if we want to move it, to well-being of all, we need to look at the same time, analyze at the same time the genetic, the SNPs, the physiology, the emotional, whatever is there for the human brain functioning. Otherwise, we are getting a real problem. And we heard, even in the previous lectures regarding clinical trials, it's not only that the clinical trials fail. Even if they succeed, there are some problems. And what I want to do in this short lecture is to show you what are the barriers. And to go through that, and hopefully, to embed you to do more, but to show you some results as well. So what do we have today? Like, this is Lee Hood who said it, and really it's more or less even nowadays that each newborn has got billions of data, will have even more, and the question is, what do we do with that? So, again, I'm quoting the lecture before that says that bioinformatics is a very essential. It's right, but it's not sufficient, because once you have the bioinformatics and you are analyzing all those SNPs and all those images and so on, could you do really prediction? Like the last question you were asked. I mean, how far can we go with it? And here we have still a big barriers, I think, in analytical, in statistics, and so on. So speaking about personalized medicine, which this meeting is all about, trying to build a personal signature. So this is a real big problem nowadays, because always, if you are speaking about pure mathematics, we'll never have enough replication. We'll never have enough groups from the same source. So one way out is to understand the mechanism. So then, you know, if we understand, we understand. But it's not that simple. So the problem is, how could we bridge that? Because like we were talking about imaging, I want to show you some examples. But I want to first relate I'll try to go very fast through all the barriers. But the first one is big versus small data. As I said, we'll never have enough identical people. Luckily enough or unluckily enough, we are different from each other. And therefore, if I really want to build the right group mathematically, according to all the mathematical and analytical tools, I will never be able to do that. But there are more failures, and I'll try to go very fast. The leakage of databases, and we'll talk about that. Hospital data is motivated. You never have there enough healthy people, so you can analyze what you can analyze, but it's not really as a prediction tool. Again, all the problems nowadays with replicability and reproducibility and so on. So there is a big criticism, lots of nature and science and other and popular science criticism, but do we have the answers? So I just want to take you following, I'm nowadays part of the Human Brain Project, so I'll give you some examples from the human brain that we are working right now. So there is a very well-known, the EDNI data bank. And the EDNI data bank is an American huge database worked out with a lot of resources and so on, and very good one. But if you look at that, and I'll try to look at that from two different points of view. One of them, it's from Thompson Lab in UCLA. He is not any longer in UCLA, but that doesn't matter. Let's look on the data. We are just looking on just one example that I wanted to show, and it's following the previous talks about imaging and so on. So we were looking on voxels vis-a-vis the SNPs. Just a very small example, and I'll come back to that. So here, just to give you the measurements, we have 500,000 measurements. I won't go into all the details. 30,000 volume changes. So in order to do it right mathematically, I need 30 billion tests of association. I will never have it. There is no way. There are not 30 billion Alzheimer patients in the world. I mean, so it happened to be that we are having a real problem. So whatever we do, so there are solutions. I mean, it's not, I just wanted to show you the problematic. So what do we do? What did we do? We found here 5 SNPs, which are the most popular one that we identified, and then we go with the p-value and so on, and that has also a lot of problems, but I don't want to go, given the short time in that, because those p-values are sometimes right, sometimes misleading, but we are playing the game. So this is just one example just to show how bad the situation is. But I want to go to another example regarding the leakage. We took this same EDNI data bank from a different point of view. It was a database that was trying to show 3 groups of Alzheimer's patients, minor cognitive impairment, and normal. And it had protein expression, and it had fat. This was the data bank, and everybody can reach that. And when I was looking at that, and we were trying to analyze this data, I'll just show you, and we did it. So just look on this graph. So the black is the missing value, because if you go into a hospital and you are suspected as Alzheimer, they give you a specific test. So if I'm trying to play the game, it's enough if I'll check if you did this specific test to tell you that you are not normal or you are normal. You know, so the prediction are based on the missing data, because the hospital data is the leakage data. It's a data that is not built with the right, as I say, theoretical measurement to analyze. And we can't do it differently. Again, we have to develop the tools that I'm getting biased data and still can take something out of that. And sure, we did, because we don't have any other. I mean, 2 of my students did it. And then just look on the cart, which everybody has on the computers, the SPSS, and just to build this clustering of trees and try to see whether you can distribute in a specific level of confidence and so on. So this is one way out of this, you know, complexity. But if we are talking about that, it's not strong enough. It's not capable enough. And the way to do it, you know, there are new tools developed every day, but more than that, my suggestion is if you take this data, even the leakage data or any other data, and you apply as much approaches that you can, you'll be always better off in a voting scheme or any other scheme. Because each statistical and mathematical and logical that I'll show you later, each one has a specific point of view. It enlarges something, it eliminates something else. And therefore, as much as you take more tools, you are providing a broader point of view. And you can balance between the two. And this is an approach that is not taken enough, because it's very hard to publish with that. Because if you want to publish very quick, take one, show the p-value. And nowadays, as absurd as it sounds, if you look on the papers, we didn't see it still today, that people are presenting in conferences, you always see this histogram with this standard deviation. Always one parameter at a time, most. And we have multi-level and multivariant, and we have all these things. But in order to prove and in order to publish as soon as possible, you better take one parameter, show that this is a strong one, did this histogram, and publish. I'm a little bit cynical, but that's part of this game that has to be changed. So this is the big criticism that is coming back and forth, you know, in all the big publication. And, you know, even The Economist went into that, and the title was Trouble at the Lab, and then The New Yorker, and we had lots of paper I didn't want to go into further. But the thing is that it's a little bit misleading, because all of a sudden, we are so bad, all of a sudden we can't replicate, all of a sudden we can't reproduce, but it's not that. It's the thing is that one and another and the third example created a big problem. The nature that I showed you earlier about neuroscience says that there it's even worse. But the main problems are, as I said, the number of replication. We always have less people than measurements. Less replication, the leakage of database, the replicability. And just I want to differentiate between the two things. Replicability is a different data, but you have to take another sample, but get the same results. And the reproducibility is those who are trying to repeat the same experiment and can't do it. And we have lots of examples about that. And now it's token more than ever. And then the confidentiality, if we really want all this data, how could we take it without, we're skipping the privacy of all those patients, even if they sign, and even if they are willing, and even if we take off the names, still we can identify them. And that's another problem that we have to fight. And then, very soon, just give me another 2 minutes. I'll do it very fast. So, as I said, we want to combine, and regarding, I wouldn't go, I thought I will be able to clinical trials. There is the FDR, the file discovery rate, that now is very used, that helps a little bit the quality of the clinical trials. I wouldn't go into that. So just to let you, we were talking about the big data, and the question is, how can I really, you know, give one example at least that we can solve it? And I'll do it very fast. So we took the same data, and the idea is really to develop, to develop a tool that can analyze at the same time imaging data or features of a picture, any picture, and at the same time physical data and categorical data and protein expression and so on. Different scales, different sources, without normalization, without neglecting part of the data, and I don't want to mention the Vioxx example. So we can't neglect. We want to take the data as is, since we don't understand yet all mechanisms, and we still want to analyze it. And I'll give just one example of my data mining algorithm, but there are many others. We took the same data. As I said, we are able to analyze data. We are less sensitive to missing value. And we want to reveal the underlying rule. It's a rule of discovery, and more than that, the unexpected rule and unexpected cases, and to be able to predict. So this is what we did, and this is the same data that I showed you with the ADNI, with the missing values. And as you can see here, I don't know how to do the pointer. Okay, so you see here the protein, and you see here the fat. So we are analyzing both the protein and the fat, and we came up with the rules, and we went back to the patient and so on. I'm sorry. I was hoping to run it in front of you so you can ask questions, but you know the technology didn't enable here the presentation and the time. So I just saw we applied it to various others, but I want to end with a message. And the message is that even though all what I talked, even though all the barriers, the way to move forward for the well-being of all of us is to look on all data, the micro and macro, the environmental, the mental, the physiology, at the same time in one hand, and to enable the open talking between the labs, between the researchers. Like if you find an hormone, let the other do. Maybe it could work as well. This has to be due to new regulations on IP and on publication, but still this is the approach. And this is, let's fly high, because this is the only way to, you know, to find the right way. Thank you. I'm sorry, sir, but I didn't know that it will happen.
Okay, is there one maybe technical question?
Wait.
Wait a second.
The modern medicine, do you prefer personalized?
I didn't hear. Just
Okay.
stay from the beginning.
If we had to choose a term to characterize the modern medicine today or tomorrow, do you prefer personalized medicine or targeted medicine or anything else?
I hope I understood. I couldn't hear you very well, but I don't think we can. We prefer one of them. We'll have to support all, because it's no way. I mean, sure we want personal, but I think we did a very nice way without personal. So on. It's always personal. As far as the doctor talks to you, it's personal, right? But really, it's a long way, but I think we'll be there. I think we have the tools, we can do that, and this is the way to do.
Thank you. Thank you, Mira.